Good afternoon, everyone. Today is Wednesday, it's not Tuesday when we have our regular chat room, but I would like to go over what we are supposed to be covering this week. So, if you have your Canvas course, October 8th, Formation of Solar System. So, we do have a few extra credits. This 6.5 extra credit is based on a chat room that I gave over the summer. Um, so take a look there and and then go for extra credit. The most you can do, better for you. And there is another one about some atmosphere detector around an exoplanet. It's still okay. I put that extra credit, I think, over the summer, so I'm using another, for another term, but it's a good one too. Um, and I I did a little restructured in in the way content is presented in the modules in a way that I do have this 6.1 introduction and objectives. I give some general review of what's going to come. And I have this archived chats as a page. If you click on it, it might show any past chats that I have given. So this is the one that has the extra credit, right? Um, this is old, and what I usually do, I keep the chats of the previous terms and I put new ones in there. So the one that is being taped now is going to be uploaded, and then when I teach this course again in the spring next year, then I will delete the summer ones and I keep the fall. So in a way, I have always the chance of providing with some updates, and then you can also kind of review other things if you are one of those students who like to see the lecture and more discussions. And then there is a 6.3, always the topic, point 3. It has the links to the reading material, but also has any extra link that I might put it that might help to illustrate the subject of that week. But in in this week, we have only a link to the book. And then the extra credit and the mandatory type of assessment. So the discussion is going on, and I will today or tomorrow morning, no later than that, I will read these discussions and start putting up some comments. So formation of solar system is probably, at least for me, when I was professional astronomer, I was working with formation, star formation basically, and with a group of stars that are still in the process of forming. The subject of formation of solar system is kind of a precedes the formation of stars. So by learning how the solar system was formed and what sort of clues or indicators you are looking for in order to better understand the formation of our solar system, those indicators, those clues can also be used to understand formation of stars in general. But the main point you should keep in mind is that stars are not eternal. You are not eternal. I don't know if you have noticed that, if you have realized that yet, but you are not eternal. You're going to be gone one day. I will be gone one day. And the same with the stars and diamonds for all that care. I mean, stars, we look at them, they seem to be the same. Every year, they seem to be in the same position. The pattern, the angular separation of stars in the sky seem to be the same. So we have this idea and this impression that the sky out there is always the same. Big mistake. Sky itself, the space, is being populated by entities that had a beginning sometime in the past. They are evolving, they are transforming the environment in which they are part of, and by transforming the environment implies they have some energy sources, they are transforming them as well. And more so, they're gonna go away, and they're gonna fulfill some role in this big stage we call universe. So stars, and we are going to learn this in during the course, more so in the next few weeks. The most important aspect of a star, at least for us, so our concern, right, the universe, we are the center of the universe. So for us, the life of a star is important because stars produce atoms, the little tiny particles we call atoms, not hydrogen or helium or lithium, maybe some beryllium. They came from the processes associated with the formation of the universe itself. But when you think about any other atoms like oxygen, we breathe, and nitrogen, we also breathe, but we don't retain. But nitrogens are important for plants. So nitrogen, calcium, magnesium, iron that runs in our blood, all these little tiny elements were manufactured inside the star. So when you think about stars and its formation and its evolution, you are really putting your hands and your fingers in the process that led to creation and formation of stuff that makes ourselves, that makes our bodies, that makes our environment the place we are. So the importance of it cannot be diminished. So this chapter is short, in fact, and it gives an inventory of our solar system. So what do you expect to find in the solar system? And I hope you are seeing what I'm seeing. Can you see this picture here? Yeah, you okay? Right?
Yeah, I can see it.
Yeah. So when you think about mass, I mean, what mass is? We in physics we associated mass with a unit kilogram, but you might you might think of grams. Here in the United States, you might make a confusion of kilograms and pounds. Pounds is not mass; it's a unit of force. It's a different quantity in physics. But mass is the stuff, is what makes up things. My table here has certain mass, has certain content that occupies certain volume, and then we can talk about quantities such as density. But for now, mass is the stuff. Atoms have mass, very tiny amount of mass, but if you think about uh, trillions of atoms, then you can think about some measurable amount of mass. But if you look at this table here, Sun has 99.8% of total mass in the solar system. And what this number is telling you is that most of the content in the solar system lies right there in the Sun, which means later on we are going to follow this process of star formation. So you have gas spread over a large volume in space. Think about 1 light years or more of tiny particles, atoms scattered all over the place, and then gravity, which is a force we studied before that crunch things in. So gravity takes over and it starts pulling all of that to a central part, where in the future it's going to be a star. And as the star contracts more and more and more, it heats up, eventually becomes self-luminous because it's so hot we can see the light coming out of it, and then we call that a star. Right? So this process of raining down towards the center, and we call center of mass, is equivalent or is associated with what we call the process of star formation. That's how stars form. In addition to this almost radial rain, you do also have a rotation going on because gas that happen to be spread in space is not globally moving in one direction. In fact, there are also rotations going on in different parts of the motion. Like if you think about a river flowing, if you look at the river flowing, you don't have a kind of a global flow in one direction. Here and there, because of the rocks in the riverbed or the margins, here and there you might see some turmoil, some little rotational edges, and those rotational edges is what I'm trying to explain as being part of the rotating gas that in addition of falling towards the center of mass is also rotating. Okay, so but most of this gas we ended up residing and locating in the star itself. But as you can see here, 0.2% of it makes up everything else. And we are part of that 0.2%, planet Earth, right? So Jupiter is zero point 0.1. Comets, which are chunk cold material that circulate the sun and orbit the sun, almost nothing. Dwarf planets, look at the percentage of dwarf planets. So our solar system has the sun, where most of the mass is. You have planets, you have satellites that goes around the planet, and between Mars and Jupiter, a bunch of rocky type of chunks, leftovers called asteroids, and you have billions or so of pieces of ices in the regions, far regions where Jupiter, Saturn, Uranus happen to be located, and even more further out, 50,000 astronomical units away from the sun, you have more of this cometary material, but the percentage is almost nothing, right? And you have some satellites and moons. Asteroids are here, and dust, cosmic dust, sometimes called zodiacal light. So as you can see, most of mass is in the sun. You have Jupiter kind of controlling some, and the other planets 4% of that remaining part. So it's not a lot, right? When we study rotation, and now that's for students who are going to probably move up to study physics and so on, so on, so on. So most of the masses in the solar system, most of the angular momentum in our solar system is not in the sun, it is in the planets themselves. Planets, they rotate, they spin, and they also go in revolution around the sun. And the angular momentum of these planets surpass the angular momentum of the sun itself, like a rotating sphere, almost in the center of our solar system. Which indicates the importance of rotation. When the gas originally was rotating, it's this initial rotation is what control and govern the flattening of this gas as the central star itself formed. But let's not go there in detail. But look at this picture here. How crazy this picture is. So you have you have the sun in the center, and in blue and in red you have orbits of some of these objects. Ceres is one of the so-called dwarf planets. Pluto is another dwarf planet. Haumea and Makemake are in Eris are dwarf planets. You have the big planets: Uranus, Saturn, Neptune, Jupiter, and then the terrestrial planets: Mercury, Venus, Earth, and Mars, and the Sun in the center. So when you look at the bluish orbit, see here, the internal orbit of Mercury, Venus, Earth, Mars, even Ceres, Jupiter, Saturn, Uranus, and Neptune, all this orbit in blue, they seem to be somewhat aligned. And when you look at orbits of the dwarf planets, Pluto included, it's not somewhat aligned, seems to be out of alignment. So how can we explain what's the takeaway information from all of that? So let's take a look at Starry Night software and explore the solar system. So this is a simulation of solar system. So you have the sun right there in the center, and the terrestrial planets, the inner planets, and also in dots you can see the asteroids. Those are the asteroids, some of the major asteroids going around. Ceres should be appearing, but it's not. But anyway, so it's almost impossible not to see all these objects as coming out of a common gas, crystallized out of a common gas, formed out of a common gas that, as we look down on it from north, this common gas was circulating in a counterclockwise direction. And this counterclockwise direction has a name. It's prograde motion, which you guys discussed a lot before. So here's the prograde motion. And there is something here going a weird way. Look at that. What that is? No, I've got a star instead of a Pallas, an asteroid. Yeah, it seems to be going in the other direction, but it's going in the proper direction it should be. See, the comet just passed by here in the simulation, and then Pallas. Another comet came by, and now Pallas is going back there. Another comet. So all of that came from the same circumstellar material. Now, if you revisit this simulation, on the outer planet, we are looking on a different vantage point, but Jupiter is there, Saturn, maybe if we expanded, you see the inner planets going the same direction there. So it's not difficult to conceive all of these material coming out of a common circumstellar gas. And I really like to show this animation. I know it's easy to find it. If you go to, not here, probably, here, there you go, EX, Pi, and videos, there you go. I would like to show this video because it gives some perspective of, let me take the sound away, of planet formation. In fact, star formation. So you have a star and you have this big circumstellar disk going around the star. Let me pause for a while. Go back there. Pause this. So the disk is rotating around the star. Some of the gas ended up finding its way to the star. So eventually, out of this material encircling the star, crystallization will take place. And eventually these crystals, these grains, will grow into what we call planetesimals. And these planetesimals will collide, coalesce, and grow into bigger objects. And eventually these bigger objects will be enough to attract other objects and gas because of the self-gravitating features, and eventually we might have, planets and their moons and so on, so on, so on. More of it right there. And this is a simulation or illustration of these grains being formed and interacting with the light of the star. In this case here, they are claiming that some of these episodes of flashing UV ultraviolet radiation might create certain types of minerals like olivine, and you might be able to see the olivine in some of the shoulders. if spectroscopy is done in the infrared. Basically, that's what's going to show here. That is some bump that indicates, some olivine in the spectrum. But the point that I want to show is what is associated with star formation, grains and circumstellar disk, and because of this common disk, you can therefore explain this almost alignment of major planets in the plane that we call ecliptic, the ecliptic plane. Now, eventually, planets are formed and planets are segregated in two broad categories. One category is called terrestrials. Terra is in fact is dirt in Portuguese, but it's also the name of our planet in Latin. So Mercury, Venus, Earth, and Mars are terrestrials in the sense that the surface of these planets are rocky type. There are more terrestrial objects we know of, like Moon. Moon is a terrestrial object because it's rocky type. And asteroids are also terrestrial objects because they are rocky type. Now, when we moved away to the regions where the gas giant or liquid giant planets happen to be located, Jupiter, Saturn, Uranus, and Neptune, they appear different. First of all, they are bigger. Second, they rotate fast. Third, they have several satellites, several moons. Mercury doesn't have a moon. Venus has no moon. Earth has one that is very big. And Mars has a couple of moons that seem to be captured asteroids. Asteroids are those rocky objects between Mars and Jupiter. So Mars seems to have captured two, Phobos and Deimos. They are less than 19 miles in extent, so they are small. But Jupiter, Saturn, Uranus, and Neptune, they have a host of satellites. Some of them formed together with the planet itself. When the planet was formed, a protoplanet formation process, as we would say, out of the material that formed this planet, some leftovers led to the formation of their natural satellites or natural moons. Some moons were captured, and that's why these gas giant planets, they might have some moons that goes in the prograde motion, and some other moons capture, they might take the other way. So they don't need to necessarily follow the crowd in the same direction as the other satellites naturally got to be formed. So when a planet captures a moon or a satellite, the satellite can ended up being in any possible rotation or revolution. That's what I'm trying to say. So let's take a look at some of these characteristics here. Terrestrial planets, if you look at the diameters, they are relatively smaller than the Jovian planets. The smaller Jovian planets, about 50,000 kilometers. The biggest of the terrestrial planets, about 13,000 kilometers. In fact, Mercury, Venus, and Earth are about the same size. Mercury is about one third of Earth size, and Mars is about half of it. Okay. Now, take a look at mass. So the mass of these planets are such that the terrestrial planets are much less massive than the Jovian planets themselves, the gas giant planets, with Jupiter being the most massive ones, about 340 or so Earth masses. So more than 300. If you take 300 Earths and put it together, you might match the mass of Jupiter, although chemical composition is different. Jupiter is primarily hydrogen and helium, and Earth has depleted hydrogen content because the hydrogen here on Earth got to be escaped long time ago when the planet itself was formed. So look at density. So the density of terrestrial planets match the density of rocks. 5.4 grams per cubic centimeter. A rock that is rich in iron, like hematite, magnetite, or limonite, these rocks, or pyrite, they might have a density that goes above 7, right? There is more iron content, the density, the content, mass per volume increase. A rocky a rock material depleted from iron content gives a less density, like Mars. If you go to the moon density looks like the density of Earth mantle, 3.5 or less. I don't have a number here for the moon. Let me check that. Moon's density. But it's about 3.3 grams per cubic centimeter. This is a rock, so you get a rock there on the floor, made of any sort of a sediments that's not rich in iron. You have the moon's density. But look at the density of Jupiter, Saturn, Uranus, and Neptune. This is kind of a bordering the water density, which is 1. Saturn is even less dense. Saturn could float on a big tub full of water, if you could imagine that happening. And then we go to the asteroids, rock type. Some of these asteroids, they collide, they create smaller objects, and some of them might find its way to our own planet, and they found in here. So meteors are, in fact, meteoroids are any piece of chunk that happen to be navigating in the regions, interplanetary regions. If a meteoroid goes in our atmosphere, it burns out, and we call that a meteor. So a meteor that happened to hit the ground, and if you collect the sample, you call that a meteorite. So meteorites are those that find their way to the museum or to researchers, and meteorites can give very good information about the origins of our solar system. They can give materials with isotope lifetime that you can use that to trace down their formations and therefore establish when the solar system itself was formed, or when these pieces of debris got fragmented, and then you can trace down the history of our solar system, basically. Let's move on to our origins. That's where it comes from. So take the solar nebula. The solar nebula was a hypothesis pretty much developed in 1700, in part because of the alignment of the planets in a plane of rotation, the plane of the ecliptic. So the planets, by that time, they knew the planets were somewhat aligned. So if the planets came from something, it was not unusual or unlikely to suggest it came from a circumstellar disk. And the central star, the sun, came also from gas. So formation of, again, the sun and its content matched the idea of a solar nebula, right? So you gotta have gas spread out there. Later on, we are going to learn this gas must be cold, can't be hot. If it is hot, doesn't collapse, gravity will not be able to overcome gravity. So some galaxies have hot gas in their intergalactic, not intergalactic, but interstellar region. And because of that, if there is any gas too hot, it's not going to form stars. So you got to have cold gas. Cold gas implies less pressure to overcome the action of gravity, which is always inward. Now, do we have evidence of planetary formation or star formation, oh yes, in this 80s and 90s, astronomers start diving into not only imaging but also into the theory of star formation and matching that theory with observation, especially when detectors efficient in the infrared and in the microwave region, not so much in radio wavelength, but microwave and infrared. These detectors were able to indicate and prove and highlight nurserings or regions of star forming uh, regions, and and then theory was brought into this field, the theory that when the stars are being formed, you have also a big composition, in fact, a big interaction with the stellar magnetic field, and the interaction of magnetism with gas give rise to a series of phenomena that astronomers start mapping and following in the 80s and 90s. So as technology grew to the point that we could map and image circumstellar disk, now um, astronomers are going down to the process of trying to establish, can we see planet forming? Can we image not star formation, because this has been done, but can we image formation of uh, planets? Can we see them being formed? And that is the next stage uh, in this subject. So what it comes after this is, and for the next and following weeks, is a closer study into planet itself. For instance, planet Earth is a planet and has a geology of its own, and the mountains and processes, geological processes we see on Earth, can also be found in other objects in our solar system, like satellites such as Io, in going around Jupiter, has volcanic activity like we do. So can we study planets as, or Earth as a planet, and establish some coherent view on how the planets were formed, how they're going to evolve, and why they are so different, why terrestrial planets are rocket type, and how Jovian planets or these gas-like planets are not rocket type. And that's the next stage. And to follow us and give us some guides through this next 2 weeks, we have to consider the sun's heat. So when the sun was formed, the heat the sun itself puts in space controls and governs the amount of material being crystallized, first of all, if whether or not there will be ices near the sun, and if hydrogen is going to be populating the inner region, because the sun's heat and the solar wind are efficient tools taking away these light elements, these volatiles, to regions where Jupiter, Saturn, and Uranus might be formed. So the sun is kind of responsible for forming the solar system the way we know, not only in its dynamics but also in its content and density and chemical characteristics. Okay, so that's it. I will stop um, taping now. Good evening, everyone.